Welcome back, my friends. We are on episode 34 of Uncertainty and Probability Theory, the Logic of Science. And we're wrapping up the first installment, I should say, of the evils and errors of epidemiology. We had two parts before this, and some of them, last week we had part two, but Part one came well before Christmas, so you might want to go back and review all that. I'm going to review a little bit right now just to make sure we're all thinking of the same things. Now, there's much more to all this. There's much more modeling to be done. We haven't even gotten near models. I'm going to mention them a little bit today. And it's going to turn out that what we've been doing all along is modeling. Probability is just a model. Remember, all probability is a matter of logic. I mean, we have proved that from scratch. We have proved that from day one. I mean, we're on episode 34 here. We've done this. This is not a year, of course, but we've been going at this for some time. We've done everything. We've taken only the barest axioms that we possibly could have. Could uncertainty be related to what we know? And the answer is yes. And that turned into probability can be related to math sometimes. And that math turned out to be a certain function, Bayes' theorem. And then when the math can be applied, it's Bayes' theorem and so forth. And from there, we went to town. Now we're going to do all the fancy modeling. We're going to come to all that. But we still haven't even learned everything we needed to know about probability. But so I threw this little segment in on epidemiology in the middle because it's important. It's always in the news. And indeed, I'm going to have in the description below, or if you're on Twitter seeing this, it's at my websites, and that'll be listed at the end, wmbriggs.com, wmbriggs.substack.com. And I'll have links to lots of other articles I've written on these things so we can look at these things in detail. I'm not going to go through the math of it and so forth today. We're just going to kind of wave our hands around, but making very important and essential points. Now, we're going to go, remember our terminology here, our notation. Y is going to be some malady. It's always, they never look for anything good. This is always a key. So Y is going to be some malady or disease or some ill effect, something that is untoward or unwanted or unpleasant or something like this. When in fact, epidemiologists could look for good things. Very rarely do they do so, though. It's always a hunt for the evil things that are causing our distresses and so forth. Not that that's a bad thing per se. I don't say that it is. But if you're never always looking for bad and never looking for the good, you're going to find the bad more often than it really exists. You're going to have a lot of false positives. X is going to be whatever background information that we have related to the problem at hand. It changes from problem to problem and setting to setting and so forth. E is going to be the exposure of some considered bad thing. We've been doing pollutants, there's pesticides, we'll mention PM 2.5, particles of a certain small size dust, essentially. Anything, could be absolutely anything. In fact, my favorite one of all time is 4th of July parades. It's a bad thing, exposure to 4th of July parades. I'll come to that in a few minutes. And dose, a sufficient dose. Now, we could have dose, could be on some sort of continuum or discrete buckets or whatever. Here, we're only, in our initial stages of looking into epidemiology, we're only considering dose as a sufficient dose that may or may not cause some malady or disease or something like this. Usually I've been saying disease. It doesn't matter what it is. The disease can even be a good thing. All of this math still works. It doesn't make any difference whether it's a good or a bad thing. All this stuff is the case. All right, so we learned that epidemiologists absolutely love to calculate the probability of exposure. I didn't even put in, I see, this is why, let me just, this isn't wrong. This isn't wrong, but it was incomplete. Okay, here we go. They normally calculate this probability here, which is the probability of exposure, given a person has the disease, or does not have the disease. They'll put a little line over it or contrary or something like this in whatever background we have. And that will be mistaken. In other words, we have the probability of exposure to whatever it is, a pollutant, a 4th of July parade, a news broadcast, whatever. That probability of exposure, given they're diseased or not diseased, will be said or implied to be equal to the probability of having the disease, having both had the exposure and a sufficient dose. And we went through many cases where exposure is not dosed, and the television example was my favorite one. If you have cable television, you get a whole bunch of channels that are paid for by your carriage fees, regardless whether you watch them. These companies still make money, part of your carriage fees. And you would be designated by an epidemiologist as having been exposed to any of these channels, even if you've never watched them, which you probably don't. There's thousands of these channels now. I don't even know how many. And some people are not exposed if they don't have cable. Cut your cable. It's a very good thing to do, save a lot of money. A dose would be if you were to watch that channel. So if you were to watch, say, CNN, if you never watch CNN, you are still exposed in these official kind of models. And if you, that is to say, if you just had it as part of your cable package, which pretty much everybody does, even if you don't watch it, and if you do watch it, you've been dosed. You have to be first exposed before you can be dosed. But the probability of being dosed, given that you have the disease or the equivalent Y, that's James's notation with the hat. That sometimes that bar over there means something else. This is just notation meaning the contrary of Y, meaning you don't have the disease. These are not equivalent to what we really want to know. This is what we always really want to know. This is it right here. You want to say the dose is associated, or you want to imply or hint that there's a causal relation between dose and the disease. You at least want to calculate this probability before you go down those lines. Even this isn't proof. If this thing is not whatever the numerical value of this is not proof of cause. This is just a probability. It's a correlation, and correlation is not causation. Everybody knows that, and I've told you a million times, all scientists know this, except when it comes to their correlation. When it's their correlation, especially when they can wave their wee p-value at you, it becomes causation to them. It's not true. It's always a fallacy. But they never cease to claim it. And they never cease making this equivalence, that the probability of having the disease given a dose and exposure is the same thing as having probability of the exposure or the probability of the dose, and it's just not true. It is just not true. The vast, vast majority of epidemiological papers that are out there make this error. They make this error. One of these two errors right here, I should say. One of these two errors. It's the same area. It's an ecological fallacy. You cannot say that exposure is equivalent to having the disease. It's just, but it's done all the time. And now we're going to take that. We did all those in the first two parts. So we did all the math and showed how that you could work all that out and come to actual numbers, which we pulled from some papers. I used one paper, but I'm going to link. I can't go over every single paper in this lecture, but there's lots and lots and lots of them that I've done over the years. I'll link to a bunch of them, and you can examine these things at your leisure, and not just dinky little ones in obscure journals on the other side of the world. Major ones used by policymakers in the United States and other countries because they don't recognize the mistakes made here. And you're suffering the effects of these policies because of these things. Okay. So that's the stuff we've done up to this point. We calculated how to calculate this, and a lot of the time we can't even calculate this because we don't have the information. It wasn't collected. It wasn't collected in the study. Sometimes we can calculate the probability of, because we can't calculate the probability of dose, because that's not usually in there. It's usually exposure, and exposure, of course, is not dose. So a lot of times we can't do this, the work that hasn't been done. But people still publish anyway because of the do something fallacy. Well, we got to publish something. We got to do something. That's another fallacy. Okay, now all of that stuff is not equal. The probability of having the disease given a dose and the exposure is also not equal to the probability of having the disease giving a model of the dose or given a model of the exposure. Because yes, indeed, a lot of times, this is just a model of, this is of dose, but you put an E in there, it's a model of the air. And later I'll just use just plain M just for notation. They don't even know whether somebody was exposed or dosed at all. And so they substitute in a model. And a model has a plus or minus to it. The model is itself a kind of probability. The details of that we'll learn much later on in this course. It's usually going to be some parameter inside of a model. It won't even be the real thing. It'll be some interior guts of the model that people make yet another mistaken equivalence and are even over certain even more than they should be. And I'm not going to, we haven't even talked about any of that stuff yet, so you just have to take my word for it for now, or you could, read ahead. You can always read ahead in Jane's or my book, Uncertainty. This is just obviously not the case. If we're only guessing whether or not a person was exposed or got a dose, we obviously don't have as much certainty of the probability of the disease given we know for a fact. Remember, this is assuming we know for a fact they were dosed and got the sufficient dose or a dose at whatever level. And we know for a fact that they were exposed, and we know for a fact whatever this background knowledge is. Here, we know for a fact that we have the model that says something, but how's the model? The real problem comes in, they don't take into account the uncertainty of the model. That should add uncertainty to this because we don't care about this. Now, we're going to go through that right now. I'm going to go through the math of this, just so you can see how that's going to be. It's pretty much exactly along the lines that we've done so far. It's just going to be a repeat of these equations. And let's see how that's going to work. So I'm going to just erase all this just to get rid of it. We've seen it before. Need the board space. So let's just modify our equation here. I'm going to, it depends on the paper, it depends on the usage. I'm just going to put an M in because sometimes it's a model of dose and sometimes it's a model of exposure before dose. It just depends on the paper and who's doing it and so forth. But it's the same. I mean, that is to say that the initial stages of this thing are the same. And it's our old friend, Bayes' theorem, which we've used many times. It's going to be the probability of whatever the malady is or disease is, given our background information. And then our model, the probability of our model. And then we repeat this. It's the probability of y given x times the probability of the model y given x plus the probability of the contrary times the probability of the model given they don't have the disease times x. Well, and there it is right there. That's simple as that. There's not that much to it. It's exactly the same thing. We could stick in a model for this kind of a thing. We know the probability. There's no problem making calculations like this. There's absolutely no problem making calculations like this. We can do it. They don't do this, though. And in fact, they substitute, they make this equivalence. They make the equivalence that this is, the equivalence, this is a not equal sign upside down to the probability of the model given y or and x. That's the same fallacy of saying the probability of the exposure or the dose is the same as having the probability of the disease. Okay. Well, really what we want, though, in we're doing these things, is we want to have the probability of we want to take into account the uncertainty of this model. And it's never done. I mean, that is to say, I'm not going to swear to that it's never done. but I've never seen it done. I haven't read every epidemiological paper out there, but the uncertainty in the model itself, the uncertainty in making the guess should be incorporated in the uncertainty. We don't want just this. We want to know the probability given that they really were dosed, or right? That's our goal. Given the probability of the disease, given they were dosed, and this, we want to basically integrate this model out. And we could do this. We could just expand. We can expand. I'm sort of hesitating because you know, this is kind of into the nitty-gritty of it. But we could expand the same thing. We could look at the equation here. We can give the probability. I'll use it as in terms of exposed. We can look at the probability of the disease, no, not the exposure, of the exposure of the disease given. Say the model is of exposure. That's the examples I'm going to be giving you in a minute. And this is the same thing. We can just calculate this through. It'll be the probability of y given mx times the probability of e given y mx, all divided by. You can see how this is going to go. Probability of y given mx, which we calculated from this step up here, because we really want to know. This is a model of exposure. We want to know, given they know they've been exposed, and here's what the model says they've been exposed. Let me explain all that. I sometimes have to rush through these things. I really should be taking maybe twice as long per video, but I know patiences are sorely tested, and that the best I can do is hope for a half an hour from you. And you can take as much time as you like reading this material. It's all going to be on the website and in my book or James's book and or various articles I have written. So let me explain all this and then give you some key insights. We start with this kind of a thing, and we start with this kind of error usually, this kind of a false equivalent. We have a model. We'll just work with exposure. We won't talk about dose right now. Just think about exposure. We don't know what exposure is, so we're going to model it. We'll throw the model in. We can calculate this. There's absolutely no problem in the world calculating this. We can calculate the probability of y given that a person was modeled as being exposed. So we're now saying the model says they were exposed, or given a certain dose, even though we're not going to talk about dose. But the model says a certain thing has happened, and we can calculate this. It's absolutely no problem. We just use Bayes' formula right here, no problem. And then we can add actual exposure in, because we want to take into account the uncertainty of this model. That is to say, we want to say we know they've been exposed, and the model said they were exposed. And we could also substitute in dose, and the model said they got that certain dose. We want these, in other words, these people were exposed and the model agreed that they were exposed, right? So that's what we were trying to say. The model is agreeing with the reality here, or the assumption of the reality here on the right-hand side. So this is, we want to take into account the uncertainty of the model. And again, that's just Bayes' theorem. We get this part right here from, this is the probability of the disease given the exposure. And we get that from this part right up here, and we just iterate Bayes' theorem. We just keep going, and we add it. Every time we add new information, we can just keep applying Bayes' theorem, and there it is. That's it. So now we can take into account here it is. Here's some of these uncertainties right here, and here's where the magic happens. So this is the probability given again of the disease given the model said they were exposed, and here's the probability of the exposure. Here's there's two pieces of magic in here. This is the probability of exposure given they're diseased, and whatever the background information is. It's the probability of exposure given the model said they were exposed. It's not 100%. There's no model out there that's going to be, well, except for the trivial, the trivial identity model that says, you know, it says exactly what when E is equivalent to M, the identity model. If we're trying to be philosophically complete here, which we are, that's a possibility in that case. This is the same thing. But this gives us some idea of the error of the model, the plus or minus of the model, because this says here's the probability of really being exposed given that they have the model said they were. And we really have, the only time this changes, this probability is not the same only when this thing right here, I hope they don't get mad at me for removing that. I'll just say here, probability y given mx. And here is its opposite down here. It's sort of opposite or contrary. The probability of exposure given not disease, no disease. This probability here, the probability of being exposed and the model saying you are exposed of the disease is only equivalent when these two things are equivalent. And this probability will only be larger or smaller depending on whether this thing is larger than this or this thing is larger than this. And these two things right here, this is the probability of the model accuracy, if you like. This says here's the probability of being exposed when the model said you would when you don't have the disease. And here's the probability of being exposed when the model said you'd be exposed when you do have the disease. And these are not frequently the same, or at least there's no a priori reason to assume they would be the same. Why should they be? None of these models, and they're statistical models, and they're very complex, and they load all kinds of crap into these models and so forth. And that's what I'm going to explain right now. Just walk through a couple of examples. These things are not the same. Therefore, there's no reason to expect this thing to be the same as this. Therefore, we can't blindly use this equation, the probability of the disease given the model, when it's entirely possible and very likely, given the experience that we've had seeing these things, this probability will be entirely different. Which anyway is so far down the stream from mainline, we don't even care. They don't even care. They just calculate something like this. They calculate the probability of exposure, modeled exposure, given the disease or not the disease. And then they say that's close enough to this, which of course is a fallacy. It's not true. It just isn't true. And this thing is not the same as this. And this is even before dose. If we expect that dose is not the same as exposure, which we've given examples already many times that they're not, we have to iterate this one more time to indicate dose. And if they don't know what exposure is, and because they can only model it, they certainly don't know what dose is. So we're really in a blind spot here. We don't know what even exposure is. We model it, but we don't even know, we can't possibly know what dose is. But yet we're going to have a confident headline that comes out and says, PM 2.5 linked with dementia, or pesticides significantly associated with autism spectrum disorder, and so forth. Now, how are they coming up with this stuff? They're coming up with this stuff because they're making this mistake. And I'm going to have at the blog and at Substack in class 34 the write-up of all this. I'm going to give you some links to some old articles I've written on particular studies, and one of them, which is I'm not going to get the exact title and the authors right here, is prenatal exposure to ambient pesticides and autism spectrum disorder. Basically what they did was this is fun. I'm not going to write this up. You just have to listen. Basically what they did is California mandates this data from the pesticide use report. People are supposed to log in somehow, and I don't know if it's individuals or corporate entities or what levels or anything like this. I'm not quite sure. But in any case, California has some kind of mandatory pesticide use reporting thing. So the authors took the results from that, and they put it into a GIS, Geographic Information Systems model. Uses things like Krieging and other things like this. And they estimated the pounds per acre per month within 2 kilometers of a maternal residence. Let me go through all that again. So we have, first of all, the uncertainty of the data coming. Remember, we have all those uncertainties. That was another error. Because we don't write them down on the equations, they somehow disappear. Like in the cases and controls and so forth, people say, well, we've controlled for cases and controls because we have wee p-values when we, no wee p-values when we compare the cases and the controls on certain demographics and biologic measures and so forth. That's not the same at all. That's ignoring it. I mean, they could stick some things in the models, but a lot of this stuff is not stuck in the models. Like what uncertainty is and goes into the pesticide use reporting. I have no idea. Is that maybe it can't even be quantified, but it's there, and we're ignoring it. We wave our hands about it, and we concentrate on the stuff we can calculate numbers for and pretend the other uncertainties don't exist. They're just washed away. This is not just the fault of epidemiologists. This happens everywhere in statistics. Anyway, so they stick that uncertain data into a GIS, the Geographic Information Systems model, which again is uncertain. All right, there's an uncertainty in that model. We're modeling exposure now. Exposure, not dose. We're modeling exposure by number of pounds per acre per month within 2 kilometers of a maternal residence. This is how we know it's not dose, because the mom, of course, has a zip code or an address or something, whatever they gave the researchers. And there it is. She has, within 2 kilometers, here is the pesticide use according to this GIS, of which there is plus or minus in both in the data and in the predictions of the GIS. And then there's also uncertainty. The mother didn't live at that residence the entire time. She wasn't there the whole time. This wasn't her real dose. Maybe it's, during the pregnancy she went off to ski in Florida or something, water ski, in the winter. Well, who knows? There's all kind of stuff that went in. There's all kinds of uncertainties in there, but they're all washed away because the one certainty, the model can be predicted with the numbers we can get out of these systems. And so therefore these numbers become reified. They become reality itself, and all these other uncertainties are just lost in the deadly sin of reification, however you want to pronounce it. So they looked at 11 pesticides. I'll just give you 2 because they're more well-known. Diazinon. And they had, I'll just write this up and then I'll explain it. 1.21, and then they looked at glyphosate, glyphos, oh for boy, spelling doesn't count. And let's see, 1.05, 1.69. And the Y was autism spectrum disorder diagnosis, which of course is a spectrum and a diagnosis which itself is subject to uncertainty. That is to say, whether a person really has, I took the cap off this, okay. That is to say, whether a person has a real, true autism and he's been diagnosed with autism, usually a male, it's not certain. It's a high probability in a lot of cases, but it's a spectrum that somebody could have mild distractions or something, and that could be from an aggressive doctor labeled as autism spectrum disorder, okay? So we have, this is too much of a catch-all term. There's uncertainty here. Then they have these odds ratio. We learned about odds ratios and so forth, and they're anything greater than 1 implicates or is toward the direction of implicating the pesticides, towards causing autism, all right? But these are so small, the differences from 1, so teeny, and they don't take into account all of those other uncertainties, including the most egregious one, the model of the dose, or the model of exposure here. And if you were to add that stuff in, this stuff would wash away. This would no longer be 1.01 or greater than 1 or anything like this. It would be something on either side of 1. I guarantee it. So they only get away with this claim, and there was a big headline, it was a big news article, that's why I ended up writing about this kind of a stuff, blaming these things and a couple of other chemicals for autism when, now, I'm not saying they don't cause autism, don't get me wrong, I don't know, I have no idea. But I do say that this kind of evidence is crap. All right, it's really poor evidence, extremely poor evidence. You can go and read about that. I'm completely out of time. There's others. Another one was residential proxy and distance to residential address proxies to freeways in autism spectrum disorders. And they chopped up the freeway, and they just chopped it up. You could live anywhere from 0 to 309 meters from a freeway, 309 to 647 meters. Why these particular? Just weird buckets, all kinds of uncertainties added up. It's the same thing. It's measuring a model for exposure. The biggest one, and the ones I had the most experience with, was the California Air Resources Board, CARB, by a series of papers with Jarrett from PM 2.5. That's the dust. Again, they looked at models of how far away people live from a highway in their models and so forth. And that became the amount of pollution that PM 2.5, what they call pollution, was dosed with. With no uncertainty accounted for in any of this stuff. It happens all the time. That's all I'm going to, this is it. I've gone over time again, as usual, and that's all I'm going to do about epidemiology for now. I'm going to say that all of these mistakes, they're very common mistakes, they're very common uncertainties, the reifications, the forgotten uncertainties, the errors, the fallacies. We haven't even got to the modeling-based fallacies, the p-values, all this kind of stuff. It's just one uncertainty after another, and most of it is unaccounted for. And the only stuff that is accounted for becomes reality, because that's what the mathematicians can calculate. And we already saw from the 2 weeks, the 2 lessons before we started this epidemiology stuff, how we should react to all this stuff. Just because we see this kind of stuff being published and touted in the news and so forth doesn't mean we have to believe it. We're able to take our own background information and stick it into our own equations. We can take their evidence, and should, and treat it for what it's worth. We should investigate each of these things as they come. And I show how to do that in the articles, and I'm going to show you how to do a lot more when we do. I'm not even sure what's going to be next week. We'll see. That we've got so much left to do. We haven't even started on cause yet, because don't forget, all these are causal claims, and we're going to see why that can't possibly be true. All right, that's it. Everything is at wmbriggs.com or wmbriggs.substack.com. It'll be in the link below, or if you're on Twitter, they'll be in the bio. You'll be able to see it there. Thanks very much for listening, and I packed a lot in again. Too much. I apologize for that. Thanks for listening.